Hey, Bill Nye the Science Guy here. When you dream about going places, where does your mind take you? Somewhere on Earth? Or to the stars? If you spend time looking at the stars, you'll notice one that's a bit red. It's actually not a star at all, it's the planet Mars. It's the next place humans are going to explore. Of course, none of this exploration could be done without science and mathematics. On this episode of NASA Connect, NASA researchers will show you how the principles of geometry are used to survey and map our planet Earth and the planet Mars. So hang tight as Vance, Jennifer, and the NASA Science Guys survey Earth and Mars on this episode of NASA Connect.
Welcome to NASA Connect, the show that connects you to the world of math, science, technology, and NASA. I'm Jennifer Pulley.
And I'm Van Hughes. Today we're here at the Virginia Living Museum in Newport News, Virginia. And right now, we're standing on a sundial, which is basically a plate marked with hour lines and a gnomon. A gnomon is a raised projection that casts a shadow from the sun. Jennifer, why don't you come be the gnomon? According to your shadow, it's time to start the show.
Well, Van, this isn't a bad way to tell time, but I think I'd rather use my watch. Throughout history, the sun and stars governed people's days, years, and even their lives. Using sundials and observing shadows was one way ancient people told time. Get this, you can even measure height and distance with shadows cast from the sun.
In fact, you can even measure the circumference of an entire planet like Earth or Mars with something as simple as a shadow.
And geometry. On today's NASA Connect, we will examine how NASA researchers use the principles of geometry to survey the world around us and the worlds beyond us.
We'll focus our telescope to see how geometry and satellites are used to measure, map, and survey other planets like Mars.
Which, by the way, can be seen quite well in this planetarium. Anyway, we'll visit some students from George Washington University who are studying and surveying the Martian landscape at NASA Langley Research Center in Hampton, Virginia.
And we'll visit a researcher from NASA's Jet Propulsion Laboratory in Pasadena, California, who will show us how geometry is used by NASA's Mars Global Surveyor. Later on in the show, students from Central Middle School in Charlotte Courthouse, Virginia will join us. They've got an awesome experiment you'll want to try.
Plus, NASA's Educational Technology Program Manager, Dr. Shelley Canwright, will introduce us to some students from Davis Middle School in Hampton, Virginia. These students are using the internet to create their own Mars surveyor. We'll learn more about this web-based activity later in the show.
Hey, as we go through the show, our friend Norbert will visit you too. Every time he appears with a cue card, that's your cue to think about the answers to the questions he gives you. Got it?
Plus, we'll go to NASA Ames Research Center in Moffett Field, California. There, we'll get all the latest information on the search for life on Mars and learn all about
green slime.
Ew. So hang tight as NASA Connect takes you on a global surveyor mission to our planet Earth and to planet Mars.
What is surveying? How do surveyors use geometry?
Surveying is the measurement of angles and distances, elevation, and direction. It's especially useful for locating property boundaries, construction layout, and map making.
Okay, Terry, can you tell me how surveyors use this equipment and geometry to survey land?
Yes, let's look at this transit. It contains a telescope, a compass, and a protractor, and it's used to measure horizontal and vertical angles. You can measure angles in the field with this and measure those same angles back at your desk with a protractor. This instrument is used to lay out objects like football fields, baseball fields, soccer fields. Today, let's demonstrate how we use this by laying out this football field.
All right.
First, we pick a starting point and set the transit over the point. We call this point corner number 1. Then we measure 300 feet to the next corner and call it corner number 4. We mark this corner with a corner marker. With 0 on the scale, we look through the telescope and line up corner number 4. We know that the angle between the sides of a rectangle is 90 degrees. So we turn the telescope towards corner number 2 until we can read 90 degrees on the transit circle or scale. Now we measure the width of the football field, 150 feet, and mark corner number 2. Next, we move the transit over corner number 2. With 0 on the scale, we look through the telescope at corner number 1 marker. We turn the telescope towards corner number 3 until we can read 90 degrees on the scale. We measure 300 feet and mark corner number 3. We now have all of the corners marked. Applying one of the basic rules of geometry, we know that the sum of the interior angles of a 4-sided polygon is 360 degrees. So, our last angle must measure 90 degrees for a correct layout. The rule for checking the angles of any object is that the sum of the interior angles of a closed polygon is equal to the number of sides minus 2 times 180 degrees. You know, Jennifer, the art and science of surveying have been used for over 3,400 years to map and measure our world. Today, scientists at NASA are preparing to measure and map the planets of our solar system.
Who knows? Maybe one day one of you will help survey Mars.
Did you know that George Washington was a surveyor before he became president? Did you know Lewis and Clark used transits on the exploration mission?
To understand angles and circumference, let's look at something we can all relate to. Pizza. Take this slice of pizza. Can you tell just by looking at it how many slices were in the original pizza and how big around it was? Sure you can. All it takes is a little geometry. A pizza usually has 8 identical slices, but not always. So let's measure the angle width of this slice. That's the part you put in your mouth first. Excuse me, sir. What does this protractor read?
The protractor reads an angle width of 45 degrees.
Right. So, what is the measurement of all the other angles touching the center?
They have to be equal or the same measurement, 45 degrees.
Right. Now, most pizzas are circular, and circles measure 360 degrees. If you divide 360 degrees by 45 degrees, the original pizza had 8 slices. Now, let's figure the circumference of this pizza. Most pizzas are measured in inches, so, using the pizza with 8 slices, if the length of the crust arc is 5.5 inches, how round is your pizza?
If there are 8 slices and the crust arc measures 5.5 inches long, then 8 times 5.5 inches equals 44 inches. The pizza has a circumference of 44 inches.
Great! Try this one. What if the angle width of your pizza slice measures 30 degrees and the crust arc is 2.5 inches? How many slices would there be in the original pizza, and what is the circumference?
I've got it. 360 degrees divided by 30 degrees equals 12 slices. 12 slices times 2.5 inches equals a circumference of 30 inches.
So, sir, would you rather eat a 12-slice pizza or an 8-slice pizza?
I'll choose the A slices. I couldn't possibly eat 12.
Did you know that over 2,000 years ago, a Greek librarian used geometry to determine the circumference of the Earth?
How did Aristophanes find the circumference of the Earth? What are the angle relationships between parallel lines and a transversal?
The concept of the Earth being a large sphere was not unknown to the ancient Greeks. And everyday observations, such as the disappearance of ships below the horizon, indicated that the Earth might be spherical or round. But how large was it? The person who figured it out was a librarian named Aristophanes, who lived in Alexandria, Egypt about 300 BC. While looking through a scroll one day, he read that at noon on the longest day of the year, a vertical column cast no shadow in Syene, a city south of Alexandria. Aristophanes knew that this did not happen in Alexandria. He thought to himself, how was it possible to have shadows in Alexandria and not in Syene at the same time of day? Aristophanes figured out that the sun must be directly overhead in Syene, but not in Alexandria. Aha! Here was proof that the Earth's surface is curved. Using a little geometry, Aristophanes set out to determine the circumference of the Earth and find out just how big it is.
Just like our pizza example, If our friend Eratosthenes could determine the central angle at the center of the Earth and the length of the edge or arc, then he could figure out the circumference of the Earth. Now, finding the length of the edge or arc was fairly simple math. Eratosthenes asked a friend to walk from Alexandria to Syene to measure the distance between the two cities. His friend estimated the distance to be around 800 kilometers, or about 500 miles. Finding the central angle, however, would take some geometry. First, Eratosthenes assumed, correctly I might add, that the sun's rays are parallel, since the sun is so far away. Check this out. In this diagram, we can see that there is no shadow at Syene, while there is a shadow in Alexandria. The line that is formed by the gnomon, or vertical column at Alexandria, and the center of the Earth, cuts or intersects the two parallel lines formed from the sun's rays. A line that intersects two parallel lines is called a transversal. The two angles formed from the transversal line and the parallel lines are called alternate interior angles. And, according to geometric rule, they're equal. Let's prove it. Take a piece of paper of any width and draw a diagonal line on it. Label the angles A and B just like this. Now, cut the paper along the diagonal so you have two triangles. Compare angles A and B by placing one angle on top of the other. Hey, what do you notice?
The angles are equal no matter what size paper you started with.
Right. When two parallel lines are intersected by a transversal, the alternate interior angles are equal. Eratosthenes was quite a geometer. From his measurements, Eratosthenes calculated the sun's rays made an angle of 7.5 degrees at Alexandria. Now, since this angle was formed by two parallel lines and a transversal, the central angle of the Earth must also be 7.5 degrees. By knowing these two things, the central angle and the distance from Alexandria to Syene, Eratosthenes calculated the circumference of the Earth. 360 degrees divided by 7.5 degrees equals 48 slices of the Earth. Are you still with me? Okay, hang tight, we're almost there. Now, if you remember that the estimated distance between Alexandria and Syene is 800 kilometers, and you multiply that distance by the number of slices in the Earth, 48, what is the circumference of the Earth? Well, if you estimated that distance to be 38,000 kilometers, you're absolutely right. Eratosthenes' estimate was really close to the Earth's circumference, which is 40,074 kilometers. His percentage error was about 5% and was probably due to an error in the distance between the two cities. 5%? That's pretty good, considering Eratosthenes used only his feet, his eyes, his imagination, and of course, his knowledge of geometry.
There are other ways that we survey the Earth which Eratosthenes never dreamed of. NASA scientists use airplanes and satellites.
But what if we wanted to survey other planets like Mars?
NASA scientists are doing that right now. But first, let's head to Central Middle School in Charlotte Courthouse, Virginia. There, students are following in the footsteps of Eratosthenes.
Hi, we're from Central Middle School in Charlotte Courthouse, Virginia.
NASA Connect asked us to show you how to do the student activity for the show. In this lesson, you will work in small groups to take accurate measurements of shadows using geometry to determine the size of an angle. Here are the materials you'll need for each group. A straight stick approximately 91 centimeters long, a meter stick or tape measure, a piece of string approximately 91 centimeters and a rocker weight, a scientific calculator, index card, compass, copies of the student data chart for each student. Let's begin. Divide the class in research groups of 3 to 5 members. Set your measurement station by first placing the gnomon perpendicular to the ground. For your measurement to be accurate, it is critical that the gnomon is vertical. To check the vertical position, tie the rock or weight to the string and dangle it above the ground in front of the gnomon. Next, measure the height of the gnomon. Place an index card under the station to mark where the shadow ends. Take measurements every 2 minutes, beginning at least 10 minutes before local noon, which is the time that the sun is highest in the sky. This will most likely not be noon, as indicated on your time measuring device. Students should note that when the sun is highest in the sky, the shadow length is the shortest. Since the edge of the shadow is fuzzy, and the shadow is moving from east to west in the northern hemisphere, be careful in deciding where to place your mark. Record your data on data chart 1. Now, back in your classroom, locate the latitude and longitude of your school location and record it on data chart number 1. Identify your best shadow length. This is the best shadow length at local noontime. Next, calculate the tangent by dividing the length of the shadow by the height of the gnomon. Locate this number, or the nearest rounded number, on the tangent table. The measure of the tangent can also be found by dividing the length of a shadow by the height of an object on the scientific calculator. Record tangent on student data chart. Make a scale drawing of your gnomon and shadow. Complete the triangle and measure the tangent with a protractor to verify your calculations. What's next, Jennifer?
Let's analyze the data by reviewing the results of this activity and by responding to the following questions. Did the weather conditions affect the results of this activity? If so, how? As the shadow lengthens over time, how will the angle be affected? If each group uses a gnomon with a different length, how will that affect the results of this activity? For more activities like this, check out our website at edu.larc.nasa.gov/connect. NASA Connect would like to give a special thanks to the mentors from the AIAA chapter at Howard University in Washington, D.C. We appreciate all your help with the student activity.
Okay, let's review. We've seen how the sun's position, satellites, and geometry help us survey the Earth. But what if we wanted to survey Mars?
Well, we don't live on Mars, so how do scientists and NASA survey the red planet?
I thought you'd never ask. Let's visit NASA's Jet Propulsion Laboratory in Pasadena, California, and find out.
What is the Mars Global Surveyor and where is it? How does the Mars Global Surveyor use geometry to survey the Martian landscape?
The Mars Global Surveyor is a spacecraft that is in orbit around Mars. Its purpose is to take pictures of Mars, to measure the temperature of the surface and the atmosphere of Mars, and to bounce laser signals off the surface of Mars to precisely determine the shape of Mars. You might think of Mars as simply being a sphere by looking at pictures of it, but to scientists it has lots of bumps and ridges. For example, the poles of Mars are so cold that the atmosphere actually condenses out to form dry ice at the poles. And as much as 25% of the atmosphere condenses out into the dry ice at the pole. So there's quite a large change in the atmosphere. Also, Mars is known for having a large bulge on the side of it, the largest volcano in the solar system, known as Olympus Mons. And so one of the functions of the Mars Global Surveyor was to measure the shape of Mars to carefully determine how big is this bulge, because it has a huge effect on the orbits of spacecraft. It's such a large bulge on the side. The way that we use geometry to convert the laser pulses into the shape of Mars, what we have to do is carefully time how long it takes for the pulses to reach Mars and bounce back to the spacecraft. And then we combine that with the shape of the orbit, which we determine by looking at how the radio signal changes as the spacecraft goes around Mars.
What is aerobraking? How does geometry influence aerobraking?
Aerobraking is when we use drag from the atmosphere to gradually shrink the orbit down. So what we had to do is use the drag from the atmosphere to gradually slow the orbit down so that it would shrink from this highly elliptical 45-hour orbit down to a very circular 2-hour orbit around Mars. This is geometry in action.
How would you like to try your hand at designing your own Mars Global Surveyor? Before introducing you to our featured EdTech activity in middle school, I wanted to give you a quick tour of Norbert's lab. You already know Norbert. He's that funny character that provides us with the cue cards and other learning activities and aids to help us understand the math, science, and technology concepts presented in each of the NASA Connect programs. His lab is your interactive link to activities and resources on the web, so you'll get the most out of NASA Connect. Just click on the rooms to enter areas like Career Corner, where you'll meet some of our guests and members of our television team. There's a study room with terms and definitions related to the show, and a page with links to other cool sites. And this is where you'll get to the online activity, especially created in partnership with NASA's Learning Technologies team. To introduce us to the web activity for this show, let's pop in on a teacher and her students at Davis Middle School in Hampton, Virginia.
Thanks, Jelly. My name is Vivian Carr, and I'm a math and science teacher here at Davis Middle School. My students love coming to the computer lab. They use it for reinforcement and enrichment of many skills in most of the content areas. Now I'd like to introduce you to Ruby Bruno. Ruby, tell us, how do you use technology?
Technology is a tool that we use in several ways: for communication with others through email, for conducting research using the internet, for writing papers and preparing electronic presentations of our work, and for participating in problem-solving online projects such as NASA Connect to reinforce what we are learning in class. In the online component for this show, we're learning what goes into the design of a spacecraft used for planetary observation. To do this, we learn about different instruments used for observing planetary surfaces from space. One of these is a camera. We get to pick out what we think are the right batteries to use, as well as the size of the solar panels required to run the spacecraft. We'll also have to consider the cost and weight of the vehicle as we try to put together the best possible planetary observer we can with all the variables given to us in the activity.
Well, Jennifer, the students here at Davis Middle School leave you and our viewers with the challenge to assemble and test their very own Mars Surveyor in a cost-effective way that produces the best results. Viewers can find that challenge in Norbert's lab on the NASA Connect website. See you on the web.
Let's head to NASA Langley Research Center in Hampton, Virginia, and meet up with some George Washington University graduate students. They are using pictures from the Mars Global Surveyor and geometry to survey Mars.
How are shadows measured on Mars? How is geometry used to determine the height of land formation on Mars?
Hey guys, I want you to meet Corey Hernandez and Brooke Anderson. They're graduate students at George Washington University. Guys, what are you studying over there?
Well, with simple geometry and shadows, we're able to determine the elevation on Mars' surface, such as a mountain, Olympus Mons, that's 3 times the size of Mount Everest, or a valley, Valles Marineris, which is the size of the United States.
Wow, those are some pretty large land formations. So, let me get this right. What you're telling me is that geometry is used to determine the elevation of land formations on Mars?
Yes, and we set up an example here for you to demonstrate this. If this is a mountain on the surface of Mars, this is a protractor to measure the angle of the sun. This is a metric ruler to measure the length of a shadow. If this flashlight represents the sun, we know that, like here on Earth, the sun is directly overhead at 90 degrees at high noon, and as the day goes on, it goes down to 0 degrees at sunset.
So, Corey, what you're telling me is this model here creates a right triangle.
The bottom leg can be represented by the length of the shadow, which we can get from taking a picture with the Mars Global Surveyor. Now, the sun makes an angle between the hypotenuse and the bottom leg. So let's pretend it's mid-afternoon on Mars. The sun would be at about an angle of 45 degrees, which, Brooke, how long is our shadow?
It gives us about 17 centimeters.
Oh, wow, so you got your angle there.
Yes. So, using our formula, remembering the tangent of 45 degrees is equal to 1, which we can find from our scientific calculators or our tangent tables, we can find the height of our mountain to be 17 centimeters. So, to double check our answer, we can see that the height of our mountain is 17 centimeters.
That's about what you calculated. That's pretty cool, Corey.
Well, I looked at Mars through the telescope, and it is definitely red. But could green slime have once existed on the red planet? That's one of the many reasons NASA Ames Research Center in Moffett Field, California is studying Mars. So now let's join researcher Chris McKay with the latest on green slime.
I'm interested in Mars, and in particular life on Mars. We know that early in Mars history it had water, lots of water. We can see the rivers and lakes that were formed by that water. The question is, when it had water, did it have life? To understand how life might have survived on a cold planet like Mars and where to look for it, we go to places on Earth where life is surviving in very cold, dry conditions, Mars-like conditions. This is a rock from the Antarctic, the dry valleys of Antarctica, the most Mars-like place on Earth. In this rock, there's life, but it's hidden inside the rock. Just below the surface, there's a layer of green. And these are algae and lichen, and they're growing inside the rock because the rock provides them a source of moisture while at the same time allowing enough light to come through. By studying life forms in these environments, we learn about the strategies that life can use in a cold, dry place. And we might apply those strategies to the search for life on Mars. And maybe we'll find evidence that there was life there when Mars was not too much colder than the dry valleys of Antarctica.
Well, looks like the sun has shifted, and that's about all we have time for today.
But before we go, Jennifer and I would love to hear from you with your comments and ideas. So why don't you drop us a line at NASA Connect, NASA, LARC, MS400, Hampton, Virginia, 23681. Or if you're on the web, email us at connect@edu.larc.nasa.gov.
We'd like to thank everyone who helped us today. The Virginia Living Museum, George Washington University, our NASA researchers from NASA Langley Research Center, NASA Ames Research Center, and NASA's Jet Propulsion Laboratory, Dr. Shelley Canwright, and especially the students and teachers from our middle school. Thanks, guys. If you would like a videotape copy of this NASA Connect show and the Educator's Guide lesson plans, contact CORE, the NASA Central Operation of Resources for Educators. All this information and more is located on the NASA Connect website. For the NASA Connect series, I'm Jennifer Pulley.
And I'm Van Hughes. See you next time.
Take the slice of pizza. Oh, you got it.
What is serving?
One of the functions of the Mars Global Surveyor was to watch it fall off.
How is geometry used to measure?
Today we'll use this
What are the angles
The sun would be at about an angle of 45 degrees.
How are shadows shout?
Okay, so tell me what you're studying over there. Welcome to NASA Connect.
Sorry, my fault.
Welcome to NASA Connect.
Sorry.
And I'm Van Hughes. Today, we're here at the... sorry. I think I see... Whoa!